Welcome back to another live stream. Now it's been a while since we've done one, but been a little bit busy the last few weeks. This live stream, instead of doing capture the flag, I'm going to be doing some advanced switching concepts, which will become a video as well. So if you happen to be watching this live stream, you can ask questions in real time as I explain concepts. Otherwise, there will be obviously a video coming up within the next couple of days as well. Going forward, starting from tomorrow, I'm going to be going back to the original schedule of capture the flags. So I'm looking forward to that. And if you have any other queries, leave a comment, leave a message. Also, put this video in 2x speed if you want. There's a lot of content to go through. So we're going to be looking at switching architecture and performance with these topics. Then we're going to be going to spanning tree protocol. Then VLAN trunking and VTP. Link aggregation ether channels. Inter-VLAN routing and SVIs. First hop redundancy protocols. Switch security infrastructure and services. And that's it. Just telling you now so that you can skip through to certain parts if you want. Otherwise, if you're going to try and learn all these concepts, then you'd want to watch this video in its entirety, rewatch. And this is based off the case study I did in network engineering video, a couple of videos previously. So if you want to see the actual commands, then you want to watch that video. Otherwise, let's get straight into the content. So with switching architecture and performance, the first thing that we need to talk about is forwarding table mechanisms. So we have a content addressable memory, CAM tables, which incorporates layer 2 forwarding. This is how the command would look in an actual Cisco interface. CAM tables operate strictly on binary logic, zeros and ones. CAM is black and white. It's 100% exact match or nothing. There is no room for ambiguity or wildcards. The exam versus textbook analogy. Traditional RAM, index at the back of the textbook to find a page number. CAM is like yelling a keyword into a room. Exact page immediately raises its hand. So we have CAM tables and we also have TCAM tables, ternary content addressable memory, layer 3 forwarding. Routing and security policies require flexibility, like matching an entire IP subnet or a range of ports. This is where TCAM comes in. Ternary means it recognizes 3 states, 0, 1, and X, don't care / wildcard. So TCAM allows the switch to evaluate longest prefix matching for IP routing packets instantly. ACLs and quality of service, it can evaluate a packet source IP, destination IP, protocol, and port flags all at the same time against a massive list of rules in a single clock cycle. Basically, to sum that up, if you have the first part of if we go back to this CAM table, let's pretend this is an IP address. If you have the first part of the IP address, and then you have a wildcard mask, it'll pretty much, it doesn't have to be an exact, it'll be exact up until that point, and it'll have other variations as well. So it allows for more flexibility, especially so if you're saying for ACLs, if you just search up, you might have different ACLs named slightly similarly. You might just do the first part of that ACL, and then a bunch of the different ones will pop up. Finally, in this part, we have line rate performance and switching routing speeds. Means a network device can forward packets as fast as the physical wire can legally transmit them without dropping a single packet. Conveyor belt demonstration. Imagine a conveyor belt moving boxes. If the boxes are huge, you only handle a few a minute. If the boxes are tiny matchboxes moving at the same belt speed, your hands have to move like a blur to process them all. The matchboxes represent the 64-byte packets. So we touched on forwarding table mechanisms. Now we're going into switching database manager. Cisco uses switch database management SDM templates to allow engineers to reallocate how fixed TCAM memory is divided. Instead of buying different hardware for different roles, a single switch model can be optimized via software profiles. Default, a balanced profile providing a mix of layer 2, layer 3 capabilities. Access, or VLAN maximizes the TCAM space for layer 2 MAC addresses and drops layer 3 routing capacity to 0, ideal for standard access layer environments. Routing optimizes TCAM space for IPv4, IPv6 static and dynamic routes, ideal if the switch is acting as a collapsed core distribution router. So if you remember the case study we did last time, you can tell that we use DLS switches and ALS switches. So you might want to prioritize access on the ALS switches and routing on the DLS switches, as an example. We also have dual IPv4 and IPv6 modifies the table to allow coexistence of both protocols, which is critical because IPv6 addresses require twice as much TCAM space, bit space, as IPv4. STM template requires a reload of the switch, just a note. Managing TCAM memory allocation distribution. An IPv4 address is 32 bits long, while an IPv6 address is 128 bits long. Because TCAM looks up at data, matching all cells with, storing a single IPv6 route or ACL entry takes up to 4 times the physical TCAM resource space of an IPv4 entry. If an administrator enables IPv6 routing without adjusting the STM template to a dual IPv4 and IPv6 profile, the switch will quickly exhaust its TCAM space. When TCAM is full, the switch enters a state called TCAM exhaustion. Instead of processing packets at line rate in hardware, access packets are dropped or sent up to the switch's CPU, causing CPU spikes, massive latency, and intermittent network failure. For example, parking lot metaphor. If an IPv4 packet is like a compact car, it takes up to 1 standard parking space. An IPv6 packet is like an oversized semi-truck. It requires 4 consecutive parking spots to fit. If you don't redesign the parking lot layout, a few trucks will completely paralyze the facility. Finally, in this section, we're going to touch on Cisco Enterprise Architecture layer functions. So we have the core layer, we have the distribution layer, and we have the access layer. Core layer, high-speed backbone. Key functions include high availability and resiliency, achieved through dual-homed redundant links, redundant power supplies, and hot swappable supervisor engines. Non-destructive upgrades. Core switches utilize technologies like in-service software upgrades. This allows an engineer to update the switch operating system on a dual supervisor with switch without dropping a single packet of production traffic. Fast switching decisions, relying strictly on ultra-fast hardware, forwarding like the CAM tables discussed earlier over fiber optic links. Interstate highway analogy. The core layer is like a 12-lane highway. There are no stoplights, no pedestrian crossings, and no police checkpoints. Its only job is to let traffic move at maximum speed from point A to point B. Now we move on to distribution layer, massive policy enforcement point and routing boundary. Key functions include route summarization, policy-based connectivity and filtering. This is where your ACL security policies and firewalls live. Quality of service, traffic is classified and prioritized here, giving voice traffic priority over web browsing, for example, before hitting the core. Inter-VLAN routing, it acts as the default gateway for the access layer VLANs, routing traffic between different departments locally so the traffic doesn't have to burden the core. Airport security and customs analogy. If the core is the airplane in flight, the distribution layer is the airport security, ticketing, and customs. It checks your ID, ACLs, weighs your bags, QoS, groups you by destination, route summarization, and directs you to the correct gate. Finally, access layer. Access layer is the edge of the network where end user devices, PC, printers, IP phones, access points physically plug in. Functions include the untrusted layer. Because anyone can walk into a building and plug a rogue device into a wall jack, the access layer is treated as inherently unsafe. Security mechanisms. Port security limits the number of MAC addresses allowed on a single port to prevent MAC flooding attacks. DHCP snooping and dynamic ARP inspection, DAI, these two topics I'll be going deeper into later in the video. Prevent rogue DHCP servers and man-in-the-middle ARP spoofing attacks. Power over Ethernet, delivering electrical power over the network cable to run devices like IP, phones, and wireless access points. Front door analogy. The access layer is the front door of a secure corporate building. You don't let people wander freely. They have to scan a badge, and if they try to bring in 50 uninvited guests through one door, the security guard locks the door immediately. Port security. Cool. So we touched on switching architecture and performance, kind of the fundamentals of advanced switching. Now we're going to go into spanning tree protocol and variants. STP elections and path selection. The root bridge election process. When a group of switches first boot up or interconnect, they have no idea what the network topology looks like. To prevent loops, they must elect a single central coordinator known as the root bridge. Every switch begins by assuming it is the root bridge. It immediately starts broadcasting configuration BPDUs, bridge protocol data units, out of all ports. Inside this BPDU is the switch's bridge ID, which consists of three parts: bridge priority, configurable value, default is 32768, extended system ID, the VLAN ID, and then we have MAC address, the switch's unique physical address. Switch constantly compare incoming BPDUs against their own bid. So every switch thinks they're the root bridge, and then they're always comparing by broadcasting BPDUs, which include bridge priority, extended system IDs, and MAC addresses. Switches constantly compare incoming BPDUs against their own bid. The rule is simple: the lowest bridge ID wins. If a switch receives a BPDU with a lower bid than its own, it stops claiming to be the root and begins forwarding the superior BPDU. The ego-driven politician. Imagine 5 politicians in a room, and they all start screaming into the microphones, "I'm the leader." They keep shouting until someone with a higher rank or status steps forward. Once a politician hears a higher ranking voice, they quiet, put down their microphone, and start repeating the leader's messages. Finding the best path. Once the root bridge is elected, every other switch must figure out the single best path to reach it. This is decided by evaluating the root path cost. As BPDU travels away from the root bridge, it accumulates a cost every time it enters an ingress port on a switch. The cost is inversely proportional to the speed of the link. So the slower the link, the more cost it takes to travel through that link. Each switch adds up the root port costs along the path to the root. The path with the lowest cumulative root path cost is elected as the primary path. If there is a tie in the path cost, the switch uses tiebreakers in this exact hardware order. Lowest sending switch bridge ID, lowest sending port priority, lowest sending physical port priority, port ID rather. Just take you a second to just digest that. The toll road metaphor. Imagine driving to a destination. Fast highways are cheap toll roads, medium roads are more moderate, and old slow gravel roads have massive tolls. Your GPS will automatically calculate the route that costs the absolute least amount of total money. STP port states and roles. To manage the loop-free topology, STP assigns specific roles to ports which dictate their operating states. So the root port, this single port on the non-root switch that has the lowest cost path to the root bridge. Designated port, the port on a network segment interface that is allowed to send frames onto that segment. So all ports on the root bridge are designated ports. Alternate backup port. The redundant ports that lose the path cost battle, they are kept in reserve in case a primary link fails. Port states, operational behavior. So you have forwarding. The port functions normally. It learns MAC addresses and forwards user data frames. You also have discarding/blocking. The port is logically shut down for user data, prevent a loop. However, it still listens to BPDUs so it can spring into action if the topology breaks. Risks. So then just before I get into the risks of automatic root bridge election, I guess I'm going to get into that right now. Risk of automatic bridge election in an enterprise network is that leaving STP to its default settings is an administrative recipe for disaster. Because the default bridge on a Cisco switch is identical, the automatic root bridge election rolls entirely down to the ultimate tiebreaker, the lowest MAC address. That means if you plug an ancient, slow legacy switch from a storage closet, for example, the network will automatically elect this weak edge switch as the root bridge. Suddenly, all high-speed core backbone traffic will detour through an old, slow access layer desktop switch, instantly bottlenecking the enterprise, exhausting its buffers, and causing massive packet loss. Think of the network as a corporate franchise. To avoid chaotic, conflicting instructions, the company establishes a strict chain of command. So you have the root bridge, which is the CEO, the ultimate boss who sets the strategy. The BPDUs are corporate memo updates. Then you have the port roles. So you have root port, the executive assistant, the one manager on each branch floor who has the fastest, most direct up to the CEO. Designated port is the project manager, the official spokesperson assigned to a specific department segment. They are the only one allowed to give orders or pass files to that department. Alternate port is the benched sub, the qualified employee kept in reserve. They aren't allowed to work or talk right now, but they wait in the wings in case a primary manager leaves. Then you have the port states. You have a forwarding state on the clock. The employee is actively working, learning names, and passing files. So names could be MAC addresses in this example, and files are user data. So who is where, root ports, designated ports, blocking state, on paid leave. The employee cannot pass files or do standard work. However, they must keep their corporate phone on to listen to memos so they know if they need to return to work. Alternate ports live here. Hopefully that makes it a bit clearer. Rapid Spanning Tree Protocol, RSCP, topology change propagation mechanisms. The process allows a strict chain of command. The switch that detects the link failure sends a specialized message called a topology change notification, TCN, BPDU out of its root port towards the root bridge. Intermediate switches receive the TCN, acknowledge it back down the chain, and forward it up towards the root. Once the root bridge hears the bad news, it sets topology change TC flag inside its regular configuration BPDUs. The root bridge broadcasts this TC flagged BPDU down to the entire network for a period equal to the max age plus forward delay, typically around 35 seconds. The magic step. When non-root switches see this flag, they temporarily reduce their MAC address table aging timer from the default 300 seconds down to the 15 seconds. This flushes old dead MAC addresses quickly without instantly wiping the memory table, forcing the switches to relearn new paths to devices. So the corporate fire alarm metaphor. Imagine a low-level worker notices a fire in a building. They don't pull the alarm themselves, which is what classic STP switches don't update the network. Instead, they run up the stairs to tell the CEO, TCN to the root bridge. The CEO then uses the building-wide intercom to scream, "Everyone clear your desks and prepare to move." The TC flag reducing MAC aging timers. RSTP port state behaviors during topology changes. Rapid Spanning Tree Protocol fixes classic STP's slow 300-second panic behavior by utilizing an aggressive proposal agreement handshake mechanism that allows the network to reconverge in less than a second, often milliseconds. When a topology change occurs in RSTP, flooding is decentralized. The switch that detects the link change doesn't wait to notify the root bridge. It immediately sets the TC flag in its own BPDUs and floods them out all non-edge designated ports. This bypasses the old chain of command bottleneck completely. The sync process. To prevent a temporary loops during a rapid change, a switch will quickly place its non-edge designated ports into a discarding state, blocking user traffic. This is called putting the ports in sync. The handshake. The switch then sends a proposal down to its neighbor. If the neighbor agrees, this is the best part, it puts its own non-edge ports into sync and sends back an agreement. The first switch immediately puts its port into forwarding. This handshake cascades through the network at hardware speed without waiting for arbitrary hard-coded legacy timers. Trustfall analogy. Classic STP is like walking down a dark hallway, taking 30 seconds to tap your foot ahead of you before every step to ensure there's no hole. Our STP is like a synchronized military squad moving through a house. The leader yells moving, the second person replies clear, and they instantly pivot to the next room together in lockstep. RSTP completely eliminates the old listening and learning port states from classic STP, collapsing them into a single, highly efficient discarding state. A lot of info there, but hopefully those analogies helped clear it up. So we covered normal STP, then we did RSTP. Now we're going to look at multiple spanning tree, MST. So MST protocol, highly scalable networking standard designed to map multiple virtual VLANs into a small number of logical topology instances. Instead of forcing a switch to calculate a separate resource-heavy spanning tree path for every single individual VLAN, major cause of high CPUs and memory overhead in large networks, MSTP decouples the VLANs from the protocol calculation. So the mail carrier analogy. Imagine an apartment building with 500 residents, VLANs. Under PVST plus, 500 different mail carriers arrive at the building every morning, each delivering one letter to one specific person. The lobby is chaotic and paralyzed. Under MSTP, one or two mail carriers arrive with consolidated boxes sorted by floor. The building functions perfectly because the delivery overhead is grouped efficiently. VLAN to instance mapping and resource utilization. And PVST stands for per VLAN spanning tree. Just to remind you guys. So to make MSTP work across an enterprise, switches must agree on which VLANs belong to which instance. This is achieved by configuring an MST region. For switches to belong to the same MST region, 3 specific attributes must match exactly across all devices. So that is the name, the revision, and the instance. And this snippet is taken from that previous video where I actually configured MST. So if you want to see that in action, you can watch that video as well. Load balancing over trunks. If you have 2 parallel trunk links connected your distribution switches, keeping one link completely blocked for all traffic is a waste of expensive bandwidth. With MSTP, you can configure the root bridge topology differently for each instance. So yeah, watch that CCNP video for the demo. But practically what we did was we assigned one instance as a priority on DLS1, and then we assigned a group of another MST as a priority on DLS2, so that one isn't sitting, so DLS2 isn't sitting idle, while DLS1 is doing all of the work. And you can watch that video to see it in action. So that's MST. Now, STP security mechanisms and toolkits. BPDU guard is an edge security feature deployed on access ports configured with portfast. Analogy, BPDU guard is a security tripwire. You only put it on doors where innocent civilians walk through edge ports. So that would be on your access layer switches down to computers that can plug in, for example, or devices that can plug in. And again, you can see it on that diagram topology that we went through in the other video. If someone tries to walk through that door carrying a heavy military hardware, the tripwire snaps, alarm sound, and the steel security door slams shut instantly, putting it into an disable mode. Under normal conditions, An edge device will never send an STP BPDU. However, if a user maliciously or accidentally plugs a rogue switch into that wall jack, the rogue switch will immediately start broadcasting BPDUs. When a BPDU guard enabled port detects an incoming BPDU, it takes immediate aggressive action. It shuts the port down completely and places it into an disabled state. The port remains dead until any administrator manually clears it or a timeout script triggers a reset. BPDU filter. So BPDU guard, which we touched on just before, is aggressive and punishing. Filter is quiet and passive. Its job is to completely stop the transmission and processing of BPDUs on specific ports. BPDU filter behaves differently depending on how it is enabled. So global configuration. If enabled globally on port-fast ports, the switch stops sending BPDUs out of those ports. However, if the port receives an incoming BPDU, filter instantly disables itself, operational port-fast is stripped away, and the port turns back into a normal STP port to prevent a network loop. Interface configuration. If enabled specifically on a specific interface, it is absolute. The port will never send a BPDU and it will completely ignore any incoming BPDUs. So, noise cancelling headphone analogy. Interface level BPDU filtering is like putting on noise cancelling headphones and a blindfold. If you stop talking to anyone and you completely ignore anyone trying to talk to you. It is peaceful, but if a network loop is barreling down on you, you won't see or hear it coming until it crashes. Production warning. Enabling BPDU filter on an interface is highly dangerous. If you connect two switches together with interface level BPDU filtering active, they will completely blind themselves to each other's existence, resulting in a catastrophic broadcast storm inducing switch loop. And hopefully that makes sense and you can visualize that happening. So we touched on BPDU guard and filter. Now we're going to look at root guard. Enforces your chosen network hierarchy. You deploy it on the designated ports of your core or distribution switches that face outward towards downstream access switches or external third-party network. So the mutiny prevention metaphor. Root guard is like a security detail assigned to watch the junior officers, so the DLS switches watching the ALS switches. If a junior officer steps up to the microphone and shouts, "I am the captain," the security detail tackles him, drags him off the stage, and mutes his microphone, root inconsistent state, until he promises to behave. If a switch downstream suddenly advertises a security BPDU, a root guard intercepts it. Instead of allowing the network topology to wrap around this rogue device, root guard instantly places that specific port into a root inconsistent STP state. While in that state, no user data frames are forwarded. However, once the rogue switch stops shouting superior BPDUs, the port automatically recovers and transitions back through normal STP states. Then we have loop guard. Protects your network against silent hardware failures, specifically unidirectional links, where a fiber optic or twisted pair cable can still transmit data in one direction but can no longer receive data in the other. So consider an alternate blocking port. It stays blocked because it is constantly listening to BPDUs from a designated neighbor. If the fiber strand carrying those incoming BPDUs suddenly breaks, the port stops hearing them. Normal STP logic dictates that if max age expires without a BPDU, the neighbor must be dead. The port will then erroneously transition into a forwarding state. Because the other strand of fiber is still physically intact and transmitting, a deadly asymmetric loop is formed. LoopGuard prevents this. If BPDUs suddenly vanish from an alternate or non-designated port due to a link anomaly, LoopGuard moves this port into a loop inconsistent state, keeping it safely blocked. So normally I don't do this, but just to demonstrate, I'm going to draw something. This is just free off the top of my head. So imagine, we'll take the color purple. Well, let's take the color brown for now. So this is a wire, okay? And with a unidirectional link, you have traffic flowing this way and you have traffic flowing this way. Normally, traffic would only flow one way at a time. So what's saying is that if one of these goes down, you're only then sending traffic this way, right? Which can cause a loop. So what loopguard does is, okay, it recognizes this due to so normal STP, all right, this is down, max age expires, neighbor must be dead, the port will erroneously, so with an error, which is the wrong thing to do, transition into a forwarding state, causing loops. So loopguard prevents this. So if suddenly vanish, BPDU suddenly vanish from an alternate or non-designated port due to link anomaly, so this goes down, loopguard moves the port into a loop inconsistent state, keeping it safely blocked. So we just close this down completely until the error gets fixed up by an administrator. Hopefully that clears it up a little bit. Mutual exclusivity rules. You cannot enable root guard and loop guard at the exact same time, exact same port and same time rather, because they serve completely opposite operational philosophies based on port roles. Cool. So that is everything to do with STP and its variants. We are now going to look at VLANs, trunking, and VTP, the meat and bones of this whole advanced switching concepts. First thing we're going to talk about is VLAN trunking concepts. So, purpose of trunking. In a segmented network, a single switch can house multiple separate virtual broadcast domains, VLANs. If you connect two switches together using a standard access link, that link can only carry traffic for one specific VLAN. Trunking solves this by establishing a single high-speed physical link between switches that carry traffic for multiple VLANs simultaneously, thanks to VLAN tagging. The multicolored sorting box analogy. Imagine you have two factories that both handle red, blue, and green bowls. If you only have standard pipes access link, you need 3 separate pipes to move the bowls without mixing them. The trunk link is like a high-speed conveyor belt that slaps a colored sticker VLAN tag onto each bowl as it enters, allowing them to ride the same belt and get perfectly sorted back into their respective red, blue, green bins on the other side. I thought that was a really good analogy to help explain. The only VLAN that isn't tagged is the native VLAN, default VLAN 1, but we will talk about that more. I definitely remember adding notes on native VLANs. So end-to-end VLANs versus local VLANs. End-to-end VLANs are legacy, which means they are pretty outdated. VLANs are geographically dispersed. A single VLAN spans across every single switch in the entire multi-building campus. Local VLANs, modern best practice. VLANs are bounded by geographic or physical limits, usually confined to a single access layer switch or single building floor. Traffic is routed at the distribution layer rather than switched across the whole campus. Comparison? So VLANs span the entire network. Users assigned to VLANs regardless of physical locations. This is end-to-end. Users assigned regardless of physical location. Complex layer 2 topology. Increased broadcast traffic across wireless access network / core. Because as you can see, there's a lot more wiring. More difficult to maintain at scale. Local VLANs. Localized to specific access switch buildings. So you have building A is floor 1 and 2 is using this switch, building B, this switch, C, this switch, building B, this switch. Broadcast traffic is confined within the local VLAN boundary. Routing handles into building traffic highly scalable and deterministic. Simplified troubleshooting and management. That's a key one because here, if let's say something happens in building A, it'll be harder to diagnose because they're all interconnected, whereas these are isolated. Something happens in building A switch, you know it has something to do with building A. Then it's just, is it floor 1, floor 2? Drawbacks of end-to-end VLANs. Flooding behavior. Because a single broadcast domain stretches across the whole enterprise, a single broadcast packet, like an ARP request or malicious switching loop, is flooded across every single trunk link and switch in the entire corporation, killing bandwidth. Yep, because they're all interconnected. Troubleshooting challenges, like I talked about earlier, pinpointing a network issue or a broadcast storm becomes a nightmare because the blast radius covers the entire enterprise campus rather than being isolated to one closet section, whatever you want to call it. Database sync and resource demands. Every switch must maintain the exact same VLAN database and run massive spanning tree instances to keep the giant multi-switch loops from bringing down the network. Town hall versus cubicle analogy. End-to-end VLANs are like a giant open concept office where one person stands up and yells through a megaphone, a broadcast packet. All 5,000 employees, for example, across the 3 buildings hear it and get interrupted. Local VLANs are like separating teams into dedicated rooms with thick walls. If someone yells, only the immediate floor hears this. Here's the kicker. If they need to talk to the other building, they have to make an intentional phone call to the router/distribution switch. Hopefully that clears it up, and I thought this analogy was pretty appropriate. Here we go. 802.1q trunking protocol and native VLAN requirements. To send multiple VLANs over one wire, the IEEE 802.1q, which is just a system standard created by this company, injects a 4-byte internal tag directly into the Ethernet frame header. This tag contains a 12-bit VLAN ID telling the receiving switch exactly which VLAN the frame belongs to. However, 802.1q introduces a unique exception called the native VLAN, default VLAN 1. Frames belonging to native VLAN are sent across the trunk link completely untagged. Because of this behavior, it is a strict requirement that the native VLAN configuration must match identically on both ends of the trunk link. Why is this? Well, if switch A treats VLAN 10 as native and switch B treats VLAN 20 as native, a catastrophic issue called native VLAN mismatch occurs. Switch A sends a frame from VLAN 10 across the trunk without a tag. Switch B receives the untagged frame and automatically assumes its native configuration VLAN 20. The result, traffic from VLAN 10, which let's say is the staff VLAN, has cleanly leaked straight into VLAN 20, which for example could be the student VLAN, without passing through a router or firewall, causing massive security vulnerabilities, data links, or dropped frames. So hopefully you can see how that is a big safety error. VLAN trunking protocol, VTP. Cisco proprietary protocol, which means it's Cisco's default protocol in this sense, used to synchronize the VLAN database across a network of interconnected switches, saving administrators from configuring the same VLANs manually on every device. A switch can operate in one of 3 primary VTP modes. Server mode. The authority, you can create, modify, and delete VLANs here. The server saves this database to its non-volatile storage, VLAN.dat, and broadcasts VTP advertisements out of its trunk ports to sync the rest of the network. Client mode, the follower, you cannot create, modify, or delete. It receives VTP advertisements from a server, updates its own running database, and forwards those advertisements along the other switches. It will actively overwrite its own database if it hears a change from a server. Transparent mode, the independent lone wolf. It does not participate in the VTP domain. You can create, modify, or delete VLANs locally, but these changes are never advertised. If a transparent switch receives a VTP advertisement from another switch, it simply passes it along out of its trunk ports without reading or syncing with it. So here's the corporate hierarchy metaphor. The server is the corporate CEO. They make the company rules, VLANs, and send out memos to everyone. The client is the mid-level worker. They aren't allowed to make rules. They just read the CEO's memo and pass it on to the next cubicle, as you can see in this first line. The transparent switch is an independent contractor. They sit in the office, take the CEO's memos, hand it to the next person without reading it and continue doing whatever they want locally, as you can see in this second scenario. Oh yep, I'll just pass it along, but I'm just doing my own thing. Few more things for VTP. Managing VTP revision numbers and safe resets. Danger zone. Every time a change is made to the VLAN database on a VTP server, the switch increments a counter called the configuration revision number by 1. When switches receive a VTP advertisement, they look only at this number. If the incoming advertisement has a higher revision number than the current database, they instantly throw away the old VLAN table and override it with a new one. VTP bomb scenario. If an engineer takes an old switch out of a storage closet where it was previously used as a VTP server and left with a high configuration revision number, say 105, changes VLAN, plugs into the production network, disaster strikes. Even if it is plugged as a VTP client, and here's the important part, it will broadcast its domain with revision number 105. The primary production core switch, sitting at revision 42, for example, will see the high number, assume it has outdated information, and instantly wipe out its own production VLAN database to match the blank or messed up database of the old storage closet switch. This instantly disconnects the entire enterprise network. So, what's the solution? Well, you have to reset the revision number to 0 safely when implementing new switches. So before plugging any switch into a network, you must reset its revision number to 0. There are two standard methods: by changing the VTP domain name to a dummy name, and then you change it back to the name that you want. Or you can toggle the VTP mode. So if you switch the device to transparent mode, and then back to a client or server, the transparent mode forces the revision number to 0 because transparent modes always have a revision number of 0. VTP deployment best practices and VTP version 3, which is the newest version. Because of the inherent risks of legacy VTP versions 1.2, modern enterprise network designs enforce strict best practices. Equilibrium rule. Once a network design is stable and all VLANs are deployed, many network architects shift all switches into VTP transparent mode. Why? Because this permanently locks the VLAN databases in place and completely immunizes the network against accidental VTP overrides. So if one switches the server, and because this is human error, one person accidentally configures the wrong VLAN, straight away, boom, all the other client switches, their their VLAN tables have changed. That's a huge, it's just a headache really, rather than a big error, because then you have to change it back. So once it's everything set, so you can do that initially to speed up the process, but once everything's in place and the cogs are running, then you may as well just change them all to transparent mode to avoid any mix-ups in the future. Again, you got to be careful because VTP mode changes the revision numbers to 0. So these are just things to think about. The power of VTP version 3. If an enterprise must use central VLAN propagation, they migrate to VTP version 3. This introduces a revolutionary security concept, the primary server and secondary server roles. In VTP version 3, switches cannot automatically update the network simply by having a higher revision number. Okay, this is important. To make a change, an administrator must manually run an explicit command on a specific switch to declare it as the active primary server. This requires cryptographic authentication, making accidental database wipes from rogue storage closet switches completely impossible. And I'm pretty sure, in fact, I can guarantee that I did this command in that case study before. So if you want to see VTP version 3 in action, you should definitely watch that video. Finally, in trunking, we looked at the basic concepts, VTP. Now we have dynamic trunking protocol, DTP. What's the difference? DTP operates using 4 primary interface modes, and the final state of the link depends entirely on the combination configured on both ends of the cable. Access switch port mode access puts the interface into permanent non-trunking mode. It ignores any DTP frames from the other side. Trunk puts the interface into permanent trunking mode. It actively sends DTP frames inviting the other side to trunk. Dynamic desirable Active negotiation. The port actively asks the other side to form a trunk. If the neighbor says yes, it also forms a trunk, becomes a trunk. Otherwise, it defaults to access. Dynamic auto. Passive negotiation. Default on many legacy Cisco switches. The port is willing to become a trunk, but only if the other side asks first. It listens for DTP frames, but does not actively initiate the request. So here's a table. If that was a lot to digest, pretty much if it's auto, it becomes access. Auto desirable, it becomes a trunk. Desirable takes precedence over auto. Remember that? And then you can look at this table for yourself, but the thing I want to talk about is limited connectivity. So trunk and access. Did I write a note on this? Yes, I did. So to understand why some traffic gets through while most is dropped, look at how each mode handles data. So this is for limited connectivity sections. The access port expects all traffic to be untagged raw data and maps everything to a single specific VLAN, usually VLAN 1. Trunk port expects traffic to be tagged with a VLAN ID header so it can multiplex multiple VLANs across the same wire. When you cross them, two things happen. So what works? Limited part. Trunk ports have a concept called native VLAN, which we talked about. Traffic belonging to the native VLAN is sent across a trunk without a tag because it is untagged. The access port can read it perfectly. If the access port's assigned VLAN matches the trunk's native VLAN, traffic for the one specific VLAN will flow successfully. However, any traffic on the trunk belonging to other VLANs will be sent with a VLAN tag. When these flag frames hit the access port doesn't understand the tagging encapsulation and drops the packets. Leaving a link in this state doesn't just block traffic, it actively degrades network health. Your switches will immediately begin generating error logs because of this protocol confusion. The fix: just never mix these hard-coded modes on an active link. If it connects to a PC or end device, set both sides to access. If it connects two switches together, set both sides to trunk. A lot of concepts there. So that was VLANs, trunking, and VTP. We only have, well, we're about halfway. Let's touch on link aggregation, EtherChannel. So EtherChannel operations and benefits, STP and EtherChannel bundling. If you connect two switches together with 4 parallel Ethernet cables, spanning tree protocol will immediately see a loop. To protect the network, STP will block 3 of those links, leaving you with only 1 active cable's worth of bandwidth. The other 3 sit completely idle, which is a problem. EtherChannel solves this by grouping up to 8 physical interfaces into a single logical interface known as a port channel. EtherChannel port channel. When you bundle these links, STP no longer sees 4 separate paths. It treats the entire EtherChannel bundle as a single logical link. Again, let's draw something. Why is the drawing tool? I think Miro is playing up. Drawing tool is not coming up, but that doesn't really matter. Effectively, hopefully you can just imagine what is going on. 2 switches, 4 links, EtherChannel. All right, this is just one, groups it into one bundle, single logical link. No blocked ports. All physical links stay in an active forwarding state. It increases bandwidth. If you bundle 4 gigabit per second links, STP treats it as a single 4 gigabit per second pipe. Instant resiliency: if one physical cable in the bundle is cut, STP doesn't trigger a topology change or recalculate. The traffic simply redistributes across the remaining 3 physical links in a millisecond. So no blocked ports, increased bandwidth, instant resiliency. Load balancing methods across bundled links. So a common misconception is that a 4-link EtherChannel acts like a single 4 gigabit per second highway where a single 4 gigabit per second file transfer can move at maximum speed. In reality, EtherChannel uses a mathematical hashing algorithm to distribute frames across the physical wires. So yeah, it's kind of split up, distributed, but all four of that frame is being moved. Hopefully that makes sense. Supermarket checkout analogy. Imagine a supermarket with 4 open registers. Links. If the store uses a bad rule like customers whose last name starts with A to Z go to register 1, bad load balancing selection, register 1 will have a massive line while the others sit empty. You want a rule that distributes the crowd evenly, like checking their exact ticket number or card size. Source to destination hashing. Configuration consistency and limits. For an EtherChannel bundle to successfully form, the physical ports on both switches must be perfectly identical twins. If there is a single mismatch in configuration, the switch's built-in protection mechanism, EtherChannel guard, will trigger shutting down the interfaces to prevent a catastrophic routing loop. Before bundling links, ensure these parameters match exactly across all member ports. Speed and duplex settings, VLAN modes, allowed VLAN list on trunks, native VLAN, and STP port cost and priority. Hardware limits. Most modern enterprise access switches cap a single Ethernet channel bundled at a maximum of 8 active physical ports, PAGP or LACP, which we'll talk about in a second. You can configure up to 16 ports in a bundle using LACP, but 8 will still sit in an active forwarding state while the other remain in a standby state waiting to take over if an active link fails. Negotiation protocols and modes. LACP, Link Aggregation Control Protocol. This is the open standard vendor-neutral link aggregation protocol. Operates using 2 negotiation modes. Active, the port aggressively initiates negotiation. It actively sends out LACP frames across the physical wire, inviting the remote interface to form a bundle. And you also have passive. The port sits in a passive listening state. It responds to LACP frames if it receives them, but it will never take the initiation to send the first LACP negotiation frame. Port Aggregation Protocol. PAGP is Cisco's proprietary link aggregation protocol because it is closed sourced. It will only work if both connected switches are Cisco devices. PAGP operates using 2 negotiation modes that mirror the logic of DTP. Desirable, the port actively invites the other side to form an EtherChannel bundle by broadcasting PAGP packets. Then you have auto. The port passively listens for PAGP frames. It wants to form a bundle, but only if the neighbor switch initiates that conversation. Again, in that case study, I configured both. So if you want to see how to configure both using the appropriate commands, switch over to that video after this. EtherChannel compatibility matrix. An EtherChannel bundle will only form if the negotiation modes match up logically. Just like DTP, if you put both sides into a passive state, the link will fail to aggregate because neither side will start the conversation. Furthermore, cross-mixing protocols is an absolute hardware failure, as we discussed why earlier. So the success matrix, active plus active, success, they both talk. Active plus passive, success, they both talk. For PAGP, desirable and desirable, they both talk. Desirable and auto, well, they both talk as well. Now we're going to look at on mode, an explicit configuration choice where you force the EtherChannel bundle to form manually, completely disabling any underlying negotiation engine. No LACP frames and no PAGP frames are transmitted or listened to. So the blind faith metaphor. On mode is like driving a car down a highway with your eyes closed because you trust that the road is straight. If there is a sudden construction barrier or a missing bridge strand, link failure, you will drive straight off the cliff because you don't have protocols, your eyes checking the environment in real time. The best practice tip is, unless a specific legacy device requires it, always use LACP active over on mode for enterprise deployments. Hopefully that makes sense. Now, layer 2 versus layer 3 ether channels. Building layer 2 ether channels on the access layer. A layer 2 ether channel aggregates multiple physical switch ports into a single logical trunk or access port. This is the most common deployment at the access layer, used to bundle redundant uplinks from an access switch to a distribution switch. When you group physical interfaces into a layer 2 bundle using the channel group command, the switch automatically spins up a virtual interface called a port channel. Because this is a layer 2 bundle, you do not need to configure an IP address on the individual physical port or the port channel interface. Here is a snippet from what I did. So you had the interface range, shut, channel group 1 mode active. So as we said before, we grouped the physical interfaces into a layer 2 bundle. Then we did no shut, interface port channel 1. This is the virtual interface, and then switch mode trunk. Instead, you manage its switching characteristics. Any configuration applied to the port channel, like setting it to a trunk or defining allowed VLANs, is automatically copied down to all its underlying physical member links. So time efficient. Configuring layer 3, the no switch port magic. When moving up to the distributional core layers, switches need to route traffic using IP addresses rather than just switching frames based on MAC addresses. So a layer 3 routed EtherChannel bundles physical links into a single logical routed link, obviously allowing you to run protocols like OSPF or EIGRP over the aggregate bundle. The absolute critical bottleneck step here is the no switch port command. By default, enterprise switch ports are layer 2 interfaces. If you attempt to assign an IP address to them, the switch will reject the command. So very similar, but you add the no switch port and the IP address that you want to assign to it. Pretty sure I go over EIGRP as well. Not sure if I cover OSPF, but if you do want to learn more about it or see it in action, you can comment and I'll do a video on that. So we just did link aggregation. Now we're going to go on to Inter-VLAN routing and SVIs. This is probably one of the more fun sections to do. So Inter-VLAN routing implementations, you have router on a stick or multi-layer switching performance. Historically, to route traffic between different VLANs, a network required a dedicated router to a layer 2 switch via a single trunk link, a topology known as router on a stick. Under router on a stick, every single packet traveling between VLANs must physically leave the switch, travel up the trunk line, enter the router's interface, get processed in software or limited routing engine, and then travel back down the exact same physical cable to the switch. This creates a physical traffic jam known as one-armed routing. Your throughput is strictly bottlenecked by the bandwidth of that single router link, and packet processing rates are low because routers traditionally rely on general purpose CPUs rather than specialized switching chips. So this is what a router on a stick would look like compared to multi-layer switching commands. The main thing here is that on router on a stick, you apply the IP addresses on sub interfaces, whereas in multi-layer switching, once you enable IP routing, you can just apply the IP addresses to the actual interfaces of those VLANs. So if you want an MLS port to act exactly like a physical router interface, MLS lets you strip away its layer 2 capabilities entirely using the no switch port command. If you try to run IP addresses on a standard switch before typing no switch port, the CLI will throw an error. So basically, like how we did in the case study, we used the DLS switches and enabled MLS on them to effectively act as routers without being routers, if that makes sense. Completely bypassing the router on a stick method for these benefits that we talked about here. and also to save time as well. So MLS eliminates this external trip entirely. It embeds a high-performance routing engine directly inside the switching hardware. Instead of crossing physical cables, traffic moves between VLANs internally across the switch's ultra-fast internal backplane via virtual interfaces called switch virtual interfaces. This allows an MLS to process packets at true line rate, pushing millions more packets per second than a traditional router and stick setup. So latency and hardware switching benefits of multi-layer switches. Multi-layer switches use hardware switching powered by ASICs, application-specific integrated circuits. Utilizing the TCAM tables we discussed earlier, an MLS looks up the layer 2 MAC destination, layer 3 IP routing destination, and any applicable ACL's quality of service policies simultaneously in a single clock cycle. The packet header rewrites happens instantly at the silicon level. So, translate a metaphor. Software switching is like an interpreter slowly looking up foreign words in a heavy dictionary page by page rather to translate a sentence. Hardware switching, ASICS, is a native speaker who instantly understands the phrase the millisecond it is spoken. Scaling benefits of distribution layer 3 downwards. Isolating access layer VLANs and controlling the blast radius. When you run layer 3 down to the access switch, each individual access switch handles its own local routing. This provides massive scaling benefits. Blast radius isolation, spanning tree protocol, STP loops, broadcast storms, and malicious ARP spoofing attacks are completely confined to a single physical access closet. The broadcast traffic cannot leak across trunk lines to cause a campus-wide meltdown. So running layer 3 down to the access switch means turning the physical links between your access and core switches into routed IP paths rather than layer 2 trunks, completely eliminating spanning tree loops. This allows the access switch to act as the immediate default gateway for its connected devices, processing and routing all local traffic right at the network edge at hardware speed. So we looked at blast radius isolation, elimination of uplink spanning tree, because the uplinks from access layer to the distribution layer are now routed layer 3 links. There are no layer 2 loops, meaning STP is completely inactive on your distribution uplinks. No port are blocked, and 100% of your uplink bandwidth is actively forwarding traffic. Faster convergence. If a core link fails, layer 3 routing protocols like OSPF or EIGRP can recalculate alternative paths using sub-second timers, reconverging the entire campus significantly faster than standard spanning tree states. The watertight submarine compartments analogy. A legacy layer 2 network is like an old open hull boat. If a leak happens anywhere, water floods the entire vessel and it sinks. Distribution layer 3 down to the access layer turns your network into a modern submarine with watertight bulkheads. If a pipe bursts in compartment A, an access switch loop, that compartment seals off automatically. The rest of the submarine continues to cruise forward perfectly. Switch virtual interfaces. So a SVI is a logical layer 3 interface configured inside a switch to represent an entire VLAN broadcast domain. So layer 2 switches have strict hardware limitations and support a density capability of only one active SVI at a time, which is used strictly as a management VLAN for remote access. SSH, Secure Shell, SNMP, which we are not going to touch on this video, but I can in future videos if you ask. The virtual router inside metaphor. Configuring an SVI on a multi-layer switch is exactly like taking a physical external router, shrinking it down into software, and plugging in its virtual cables directly into the internal VLAN corporate board. So multi-layer switches possess a hardware routing engine that supports a high density capability of hundreds of concurrent active SVIs, allowing them to act as the functional default gateways for multiple local subnets and VLANs across a campus network. SVI line state dependency calculations. For an SVI, let's take an example, interface VLAN 10, to transition to the up state, the switch evaluates a strict dependency calculation. The SVI will only come up if the VLAN itself exists in the switch database and is active. The VLAN features at least one physical port that is concurrently in an up operational state. This physical port must be actively forwarding traffic. It cannot be blocked by a spanning tree protocol or disabled by port security. Empty classroom analogy. Imagine an SVI as a high school teacher. If at least one student, an active physical device, walks into classroom 10, so VLAN 10 for example, the teacher stays and conducts the lesson. The SVI turns up. If the last student packs up their bag and leaves the room, the teacher turns off the lights, locks the door, and goes home. The SVI drops down. Preventing routing black holes. SVI line dependency is a fail-safe mechanism that prevents routing black holes by ensuring a virtual interface automatically shuts down if it loses all physical connection to its assigned VLAN. Without this calculation, a switch would keep its SVI up and blindly advertise dead routes to upstream routers, causing packets to be permanently dropped. With it, the moment the final physical link in a VLAN fails, the SVI immediately drops to a down state, prompting routing protocols like OSPF to quickly remove the dead path and reroute traffic through an alternate route. Broken bridge metaphor. Imagine a GPS app managing traffic. If a bridge collapses, you want an app to register it instantly so cars detour. If the app keeps insisting the road is open, hundreds of cars will drive straight off the broken ledge into the river, the black hole. The switch port autostate exclude command. The switch port autostate exclude command solves a specific routing issue caused by permanently connected devices like network monitoring probes or IDS sensors. Normally, an SVI stays active as long as at least one physical port in that VLAN is up. If monitoring a device stays plugged in after all regular users leave, it keeps the SVI artificially alive, causing upstream routers to incorrectly send traffic to an empty VLAN. Applying switch port autostate exclude forces the switch to completely ignore that specific port during its line state calculations. If all user links drop, the SVI will shut down instant to protect the routing topology regardless of the active monitoring link. The security guard analogy. So back to the classroom metaphor, the teacher stays if a student is in the room, but what if a night janitor or security guard is sitting in the back corner of the room checking the fire alarms? They aren't a student, they shouldn't force the teacher to stay all weekend. Running switchport auto state exclude is like telling the teacher, ignore the security guard, when the last student leaves you can go home. So that was inter-VLAN routing and SVIs. Now we're going to look at first hop redundancy protocols. Only two more topics to go. So we have first hop redundancy protocols, then switch security infrastructure and services. So let's start with HSRP, hot standby routing protocol. The HSRP preemption mechanism by default is non-preemptive when a group of multi-layer switches or routers form a HSRP standby group. They look at their configured priorities, default 100. If the device with the highest priority wins that election and becomes an active router, taking ownership of the virtual IP and virtual MAC addresses to forward user traffic. The primary active switch experiences a power failure or reboots the standby switch takes over the active role seamlessly. However, when the primary switch boots back up and rejoins the network, it will not take back its job by default. Even if its priority is significantly higher than the current acting router, it will sit idly in a standby state. To force the primary switch to automatically resume its rightful role as a primary forwarding path, the moment it recovers, you must explicitly configure the standby group preempt command. So in that example, you can see it's as simple as just standby 20 preempt, standby 100 preempt. Substitute teacher metaphor. Imagine a world-class tenured professor. Primary active router gets sick and substitute teacher, standby router, takes over the classroom. When the premier professor walks back into the school, completely healed the next day, they don't get to teach. They have to sit in the back of the room and watch the substitute finish the semester. Configuring preempt is like giving the professor the explicit authority to walk in, tap the substitute on the shoulder and say, "I'm back, thank you, the classroom is mine again." So aligning HSRP topology with spanning tree protocol. For a network to run at peak efficiency, your layer 2 topology, spanning tree, and your layer 3 topology, HSRP, must be perfect mirror images of each other. For any given VLAN, the switch configured as the HSRP active router must be the exact same physical switch configured as the spanning tree root bridge. The mismatch trap, suboptimal path. If a switch A is the STP root bridge but switch B is the HSRP active router, a user sends a packet to the default gateway, HSRP virtual IP owned by switch B. Because switch A is the STP root bridge, all physical layer 2 links block loops by funneling frames towards switch A first. The frame leaves the user, travels up to switch A, passes across the internal trunk link to switch B just to reach the gateway, and then routed out. This behavior is known as asymmetric routing or traffic tromboning. It wastes valuable trunk link bandwidth and introduces unnecessary latency. Final concept for hot standby routing protocol is interface tracking metrics and priority decrements. HSRP natively only monitors its own health and the status of the local VLAN interface. It has no idea of its upstream links leading to the core internet. I'll repeat that again. It has no idea if its upstream links leading to the core internet are dead. If switch A is the HSRP active router, but its core WAN uplink breaks, it will continue to blissfully act as the active router, attracting user traffic and dropping it straight into a dead-end black hole. Interface tracking solves this by allowing HSRP to spy on the operational state of specific external interfaces. So for example, in that case study that we did, we can see here, this purple section, this is the upstream link. If this goes down with that X, as you can see, HSRP automatically will assign DLS2 uplink as the new sort of path that the data will flow through, instead of all just continually flowing through DLS1 to the gateway, because there's no way to reach the gateway from this link. This link has gone down. HSRP, Cisco proprietary protocol that elects a single active router to forward traffic and a single standby router as backup, requiring a manual configuration to reclaim its primary role after a failure. In contrast, VRRP is an open standard protocol that elects a master router and supports multiple backup routers, allowing the virtual gateway to reuse a physical interface's real IP address and automatically enables preemption out the box. So these are the side-by-side configuration differences. As you can see, the main one is obviously standby and VRRP, but the preempt is not needed for VRRP. Now we're going to move on to gateway load balancing. So gateway load balancing virtual gateway architecture features. Under HSRP or VRRP, an entire subnet shares a single virtual IP and a single virtual MAC address, meaning all client traffic is forced down one physical path. GLBP changes the architecture completely. A GLBP group still shares a single virtual IP address, which configures as the default gateway on the all client PCs, However, instead of just using one virtual MAC address, GLBP automatically hands out multiple distinct virtual MAC addresses to different routers within the same group. When client devices send out an ARP request to find their default gateway's hardware address, the GLBP network intercepts the request and strategically replies with different virtual MAC addresses depending on the client. This allows all routers in the group to actively forward traffic simultaneously under a single gateway IP configuration. So in action, let's take the scenario. In GLBP, router 1 acts as the sole receptionist, AVG, meaning it handles 100% of the incoming ARP setup calls for the gateway, while router 2 purposely stays silent. However, when client 2 asks for the gateway address, router 1 tricks the client by handing out router 2's unique virtual MAC address. From that moment on, client 2 stamps all of its actual internet data packets with router 2's MAC, causing the switch to steer all of the heavy payload traffic directly to router 2 for routing. This perfectly splits the labor. Router 1 does the talking to distribute the workload, while router 2 does the actual heavy lifting of the moving client 2's data router without router 1 ever touching a single packet. So, why it is important for clients to send ARP requests? Computers are fundamentally layer 2 devices. When talking to their immediate neighbors, even though you configure a client PC with an IP address for its default gateway, a network card cannot wrap data in an Ethernet frame without a destination hardware MAC address, layer 2. The ARP request is the critical bridge between these layers. When a client wants to send a packet to the outside world, it triggers an ARP broadcast asking who has the gateway IP, send me your MAC. In a standard network, this simply retrieves a single hardware address. In GLBP network, this ARP request is the exact trigger point that allows the AVG to intervene, run its load balancing algorithm, and strategically hand out different AVF MAC addresses, dynamically splitting the network's traffic across multiple physical routers without the clients ever realizing it. A lot of info for Gateway Load Balancing Protocol, GLBP. So stay with me, we're almost done. But this was definitely the hardest to wrap your head around and sort of prep for, but it'll start to make sense as we finish up. So the role of the default gateway. The default gateway acts as the local exit door for your computer. Its primary role is to serve as the intermediary router connecting your local home or office network, LAN, to the rest of the digital universe, the internet or other remote networks. When your computer wants to talk to another device, it checks the destination IP address. Same network, if the destination inside your local network like printer or next room, your computer talks to it directly using layer 2 MAC addressing. Different network. If the destination is outside your local network, like Google servers, your computer realizes it has no direct physical path to get there. It blindly packages up the data and sends it directly to the default gateway, trusting the gateway knows how to route it across the globe. Why it is beneficial for the computer to gain the gateway IP. A computer cannot function on the modern internet without learning its default gateway, usually assigned automatically via DHCP when you connect to Wi-Fi. Here is exactly why gaining that IP is so critical. It breaks down the local boundary. Without a gateway IP, a computer is completely isolated within its own local subnet. It can talk to other PCs on the same switch, but it is entirely blind to anything beyond them, meaning no web browsing, no cloud services, and no external emails. So it solves the where do I go dilemma. A typical computer doesn't have the processing power or memory to keep track of a map of the entire internet. By gaining the gateway IP, the computer only needs to know one single rule. If the destination isn't local, send it to the gateway IP. It offloads all the complex mapping and routing destinations to the router. It triggers the essential ARP process. As soon as the computer knows the gateway's layer 3 IP address, it can fire off an ARP request to find the gateway's matching layer 2 MAC address. Once it has that hardware address, it can successfully build the physical Ethernet frames required to actually push its data off its network interface card and out into the wider world. So what does AVG and AVF stand for? So maybe something you were wondering about. AVG stands for Active Virtual Gateway. This is the single elected boss or receptionist router in the GLBP group. Its job is to listen for client ARP requests and assign them different virtual MAC addresses to distribute the workload. AVF stands for Active Virtual Forwarder. This is the operational role given to all routers in the GLBP group. An AVF's sole job is to accept, process, and physically route the actual data packets sent by the client. So the Maître d' and the chef's metaphor. I'm pretty sure this is some French thing, but anyway. The AVG is the restaurant's Maître d' standing at the front of the door. He doesn't cook any food. His only job is to greet hungry customers' ARP requests and tell them exactly which table waiter to go to. The AVFs are the chefs working hard in the kitchen. They don't talk to the customer at the door, they just cook the food for the packets that the Maître d' sends directly to their specific kitchen station. So we have the AVF and we have the AVG. So gateway load balancing protocol mechanisms. The AVG can distribute those unique virtual MAC addresses to clients using 3 built-in mathematical allocation methods. You choose the method based on your campus traffic profile. Round robin, which is the default. The AVG distributes the virtual MACs sequentially. Client 1 gets forwarded 1's MAC, client 2 gets forwarded 2's MAC, client 3 gets forwarded 3's MAC, client 4 loops back to forward 1. This guarantees a perfectly equal distribution of clients across all paths. Weighted. This method looks at a manual configured weight value assigned to each router interface. If router A has a high bandwidth fiber connection, you give it a higher weight. The AVG will deliberately hand out router A's virtual MAC more frequently than a lower weighted backup router, ensuring powerful hardware carries the bulk of the corporate data load. Host dependent. The AVG tracks the specific hardware MAC address of the requesting client machine and guarantees that the specific client host will always receive the exact same virtual MAC address every time it ARPs for its gateway. This is critical for environments where stable, predictable state connections or firewall mappings are mandatory. Finally, the very last point, but there's still a lot of info to go through. Perhaps the most important out of everything for cybersecurity, switch security, infrastructure, and services. Infrastructure services and port authentication. The first thing that we'll look at in this section is NTP operational modes. Network time protocol synchronizes the clocks of network devices over packet-switched variable latency data networks. It ensures log files across the enterprise match precisely, which is critical for security forensics and troubleshooting. NTP operates using distinct organizational modes. So we have server, client, peer, broadcast, multicast, and master or local master. Server. The authoritative time source. It synchronizes its own clock with an upstream reference clock like an atomic clock or GPS and responds to incoming time requests from clients. It never alters its time based on client packets. The client, the receiver. Client periodically sends NTP requests to a designated NTP server, calculates the network propagation delay, and adjusts its internal clock to match the server. Peer. A bidirectional horizontal relationship. Two switches or routers running as peer exchange time packets to sync with each other and provide backup time agreement in case the primary upstream server link goes down. Broadcast and multicast. High efficiency distribution. A server pushes out time synchronization frames to a local subnet broadcast or multicast address. Devices listen passively. This reduces processing overhead because the server doesn't have to answer thousands of individual client requests. It's master or local server, a fallback command used on a router switch to tell its own internal quartz crystal clock as an authoritative NTP stratum source if it completely loses connection to the internet or outside reference clock. Log correlation importance. If a hacker compromises the network at 1:05 a.m., but your firewall's clock is 4 hours fast and your Active Directory server is 2 hours slow, correlating the logs to trace the attack chain becomes an impossible puzzle. So that's NTP, Network Time Protocol modes. Server, client, peer, broadcast, multicast, and master. Legal necessity of message of the day login banners. A legally sound MOT banner must explicitly prohibit unauthorized access, warn that all activities are monitored, and state that evidence will be provided to law enforcement. Strictly avoiding welcoming language like welcome or hello to prevent intruders from claiming they had an implicit invitation to enter the network. Example, unauthorized access to this network device is prohibited by law. All connections are monitored. Evidentiary logs will be provided to law enforcement agencies. If you're not authorized, disconnect now. Yeah, and to configure that, you just write banner MOTD and then you use a symbol to initiate the start of the message. So that could be a hashtag, and then you write your message. So the message that we just wrote, and then you would finish by writing a hashtag at the end to signify that the message has been completed. IEEE 802.1x standard. A port-based access control framework that keeps switch port locked until a device is authenticated, operating by 3 specific roles. The supplicant, the client device like a laptop requesting network access, the authenticator, the gateway, switch, or wireless access point that acts as a proxy middleman, passing credentials along and physically opening or closing the port based on the final decision, and the authentication server, the backend authority database, typically a radius server that validates the credentials and issues the final accept or reject verdict. So we have the assigned parking lot spot analogy. Rather, actually, that is for port security. So we will come to that in a second. So it's pretty much the standard. You have the supplicant, the authenticator, and the authentication server. Pre-authentication traffic exceptions. To solve the paradox of a locked port needing to transmit login data, the AO2.1x framework permits a strict exception list of low-level traffic to pass through an unauthorized interface. While standard user data like web or email traffic is completely blocked, the switch keeps its ears open for EPOL, EAP over LAN, the specific protocol frames carrying the user's login credentials, to the switch. STP Bridgeport data units. Spanning tree messages required to continuously monitor and prevent network loops. CDP and LLDP, discovery protocols that allow the switch to identify the attached hardware, such as an IP phone, before anyone even authenticates. So basic foundations, LAN, local area network, what it means, a private, high-speed computer network that connects devices within a limited physical geographic area, such as a single home, office building, or university campus. Spanning tree protocol, a layer 2 protocol designed to prevent loops on the network. It maps out your network connections and strategically blocks redundant paths so broadcast traffic doesn't circle the network infinitely and crash your switches. The authentication duo, EAP and EAPOL. So EAP, Extensible Authentication Protocol, is a flexible authentication framework Rather than a single rigid mechanism, it defines how security credentials, passwords, certificates, tokens are formatted and exchanged between a device and a verification server. So what it means, the specific vehicle used to carry EAP security messages across a local wired or wireless connection. Because EAP is a high-level framework, EAPOL acts as the physical encapsulation method that allows an unauthenticated laptop to talk directly to a switchboard. The Neighbor Discovery Protocol, CDP, Cisco Discovery Protocol, is a proprietary layer 2 protocol that allows directly connected Cisco devices, routers, switches, IP phones to share information with each other. It advertises data like the device name, software version, and capabilities. LLDP, the industry standard equivalent of CDP. It performs the exact same neighbor discovery function as CDP, but is completely open source, allowing hardware from different vendors like Juniper Switch and HP Printer to see each other. Now we're going to move on to multi-factor authentication. True MFA requires users to verify their identity using tokens from completely separate architectural categories. Using two factors from the same category does not qualify as true MFA. So these validation factors are divided into three distinct categories. Something you know, information you recall, such as passwords, pins, or security questions. Something you have, a physical or digital object you own, such as a hardware, YubiKey, smart card, or smartphone authenticator app. And something you are, unique biological or biometric characteristics such as fingerprints, facial recognitions, or iris scans. Then we have AAA protocol attributes. The AAA framework handles security via authentication, identity, authorization, permission, and accounting logging, using Radius as its standard transport protocol. Radius features three critical architectural traits. UDP, it runs on, so UDP is unidirectional port transport. Remember we talked about UDP before? Runs on ports 1812 and 1813 for fast low overhead communication. Combined functions. It merges authentication and authorization into a single transaction, returning a user's permissions embedded inside the login approval packet. Partial encryption security risk. It only encrypts the password field using MD5, leaving usernames, device profiles, and accounting commands in clear text, which often requires modern deployments to wrap Radius traffic inside secure TLS or IPsec tunnels to prevent packet sniffing attacks. And I covered TLS in my recent video, what happens when you type google.com into a web browser, so you can watch that video as well if you don't know what TLS is. So, package security contrast. Radius is like a security guard carrying an unsealed, clear plastic briefcase down the hall. Anyone looking at the briefcase can read the documents inside detailing who you are and what room you want to enter. The only thing hidden inside the briefcase is a tiny locked safe containing your password. Contrast this briefly with TACACS+, which encrypts the entire packet payload to hook advanced viewers. Port security and traffic controls. So MAC limits and address tracking. By default, an access switch port will happily learn thousands of unique MAC addresses and store them in its CAM table. Port security restricts this behavior by allowing you to define a maximum limit on the number of unique MAC addresses allowed to transmit traffic through a single physical interface. The switch can track and store these authorized addresses using three distinct methods: static, dynamic, and sticky. Static is pretty much that the administrator manually types the specific hardware MAC addresses directly into the interface configuration string. These are saved in the running configuration and remain permanently. Dynamic is the switch learns the MAC address on a first come, first served basis from the first active frame that hits the port. These addresses are stored only in volatile RAM. If the switch reboots or the link drops, this memory is completely wiped and the port will dynamically learn the next address that talks. Sticky. The ultimate real-world hybrid approach. When enabled, the switch dynamically learns the MAC address of the attached device and it instantly writes it directly into the running configuration file as a static entry. If you run the copy running config startup config command, these dynamically learned addresses become permanent across reboots, eliminating the need to type out dozens of characters manually. Assigned parking lot analogy. Static is like painting an employee's exact license plate number onto a parking space. Dynamic is like saying the first car to park here gets the spot for the day, but when the gate closed tonight, it's open season tomorrow. Sticky is like letting a car park dynamically, but the moment it shuts off its engine, a security runs out and permanently bolts a plaque with their license plate onto the asphalt. Asphalt, rather. I mean, if you've made it this far, surely leave a comment, leave a like. Not that I necessarily am looking for major viewers or anything like that. I'm doing this to, one, help consolidate my own learning, and two, if you are watching these type of videos, it means that you are really into cybersecurity concepts. So I'm trying to build a community of like-minded individuals where we can discuss cybersecurity content, but that's obviously a long-term ambition. But yeah, I knew this was going to be a long video, so I'm powering through for you guys, if anyone is watching up to this point. So now we have violation modes. We touched on port security, violation modes. If a port reaches its maximum MAC address limit and an unauthorized rogue device attempts to send traffic through a port security violation occurs, the switch responds based on its configured violation mode. So you have protect, which is the silent defender. The switch drops all traffic originating from the unauthorized MAC address. However, it permits traffic from the original authorized MAC to continue flowing normally. No syslog notifications are sent, and the interface status counter does not increment. Violation restrict, the talkative defender. Like protect, it drops the rogue frames while allowing authorized traffic to pass. However, it proactively sends a syslog SMP trap notification to the administrator and increments the interface's security violation counter. Shutdown is the hammer. The moment a rogue MAC hits the port and the switch takes immediate drastic action, it shuts the entire interface, dropping all traffic, even from legitimate user, logs a critical error, and places the port into an disabled state. So, security guard metaphor. Imagine a secure building entrance. Protect is a guard who quietly taps a stranger on the shoulder and says, "You can't come in," while letting employees pass. Restrict is the same guard, but they pull out a megaphone to yell, "Security intrusion at the front gate," while blocking the stranger. Shutdown is a panicked guard who slams down a master emergency lever that drops massive iron blast doors over the entire entrance, locking out the stranger, the employees, and the deliveries altogether. Aging behaviors. To prevent ports from locking out legitimate devices permanently when hardware changes, you can configure port security aging. Absolute. The secure address is automatically deleted after a fixed timer expires, forcing the switch to re-verify the device. Inactivity. The timer only counts down if the attached device goes completely silent. If the device is actively sending frames, the timer continually resets to full health. If the device is unplugged and inactive for the duration, its address is cleared, allowing a new device to connect. Resolving an error disabled state. When an interface enters the disabled state, turning the indicator light solid amber due to errors like port security violations, the link goes completely dead. Administrators can revive the interface using two primary methods. So you have manual reset sequence. An engineer must access the interface via the CLI and manually run shutdown to flush the error from the logical register, followed by no shutdown to force the hardware engine to reevaluate the link. Automated recovery tools rather. To save time, engineers can configure the error disable recovery engine by specifying an error cause and setting a countdown timer. Once the timer hits 0, the switch automatically clears the error state and restarts the interface without human intervention. Traffic storm control thresholds and packet handling. When an overwhelming flood of broadcast, multicast, or unknown unicast BMU packets, usually caused by physical loops or failing hardware, exhausts switch buffers and paralyzes the LAN. Storm control prevents this by providing hardware-level rate limiting on access interfaces using two specific thresholds. So you have the rising threshold, the maximum bandwidth limit. If incoming BMU traffic spikes past this ceiling, storm control immediately blocks and drops the flooding data at the hardware boundary. Falling threshold, the recovery floor. Once triggered, the switch continues to aggressively drop traffic until volume falls completely below this lower limit. This safety gap prevents the interface from flapping, rapidly toggling between blocked and unblocked states every millisecond. I wish I had a diagram. Can I? There we go. So what I'll do is I can draw it out for you guys. So there. So this is the upper threshold at 80%. And this is the falling threshold. So normal traffic occurs between this area, right? But once this reaches above, the storm control aggressively drops it will aggressively drop traffic, not to safe to normal levels, but it will aggressively drop to below the falling threshold to prevent the interface from flapping, blocked and unblocked states every millisecond, before just going back to usual flowing state, if that makes sense. Give me 1 second before I power through and finish this off. Okay, 3 more topics: network attacks and mitigation techniques, private VLANs, and access control lists. All very important things. So you have port security, MAC limits, and address tracking. By default, an access switch port will happily learn thousands of unique MAC addresses and store them in its CAM table. Port security restricts this behavior by allowing you to define a maximum limit on the number of unique MAC addresses allowed to transmit traffic through a single physical interface. Whoops, I redid that one. Network attacks and mitigation techniques. Yeah, it's getting long. Been talking for nearly 2 hours, but I'm going to power through. A MAC table, address table flooding attack occurs when an attacker bombards a switch port with thousands of randomized source MAC addresses, rapidly exhausting the physical memory of the switch's content addressable memory CAM table. The downstream impact. Once the CAM table is completely full, the switch can no longer learn legitimate addresses and reverts to a fail open behavior. This allows flooding all incoming traffic out of every single port in the VLAN like a dumb network hub. This allows the attacker to easily sniff and capture sensitive private data frames across the network. Mitigation strategies. This attack is neutralized by enforcing port security, setting a switch port security maximum cap on allowed MAC addresses per port, and enabling MAC move notification to alert administrators if a MAC address is rapidly jumping between interfaces. So this is the guest registry analogy. Imagine a secure corporate building with a guest book at the front desk. A prankster runs inside and rapidly writes 50,000 fake names into the book, filling every single page. When a legitimate employee walks in, the guard can't log their name anywhere. Having given up on sorting who is who, the guard just opens all the office doors and lets anyone roam anywhere they want. So that is MAC address table flooding, which can be mitigated with port security. DHCP snooping, a layer 2 security mechanism that mitigates man-in-the-middle attacks by preventing rogue DHCP servers from handing out malicious IP configuration to network clients. It configures the network using 3 core components: trusted versus untrusted ports. Interfaces are split into trusted ports connected to legitimate upstream servers, allowed to send all DHCP messages, and untrusted ports connected to end users. If a server-side message like a DHCP offer enters an untrusted port, the switch instantly drops it to block the rogue server. The binding database. The switch dynamically builds a live source of truth table by tracking legitimate leases on untrusted ports, logging each client's MAC address, leased IP, lease time, and physical port VLAN. Then you also have option 82 support. The switch injects location metadata, switch ID, and exact physical port directly into client requests, allowing central DHCP server to assign precise location aware IP addresses based on where the device is plugged into the building. So this is the mailroom courier analogy. DHCP snooping acts like a mailroom inspector. Mail coming from the corporate executives' trusted ports can contain building instructions and keys, IP addresses, but if a package arriving from a standard cubicle desk, untrusted port contains a master key claiming to be from the CEO, the inspector throws it in the shredder immediately. Then we have DHCP helper addresses, IP helper address. The IP helper address function overcomes a standard architectural barrier where routers block the broadcasted DHCP requests of client bootloaders at the layer 3 boundary, preventing them from reaching centralized DHCP servers located on different subnets or VLANs. The problem. A client broadcasts a DHCP discover message, DORA, discover offer request acknowledge, which hits its local default gateway, SVI, or routed interface, and instantly drops to prevent network congestion, isolating the client from central router. The solution: by configuring IP helper address with the server's IP on inbound interface, the router intercepts the broadcast and performs a live modification. Repacking the payload onto a target unicast UDP message, port 67, sourced from the interface's own IP. The result, the router safely routes this unicast packet across the network's backbone to the central DHCP server. The server checks the gateway address field GIADDR in the payload to identify the source subnet, selects the correct IP pool, and sends a unicast reply back to the router to deliver the client. The megaphone to phone call metaphor. Imagine a person standing in a room shouting through a megaphone, "I need a job assignment," broadcast. The server is in a soundproof building 3 miles away and can't hear a thing. The default gateway router stands next to the person, listens to the megaphone shout, pulls out a cell phone, dials the centralized server room directly unicast, and says, "Hey, I have a guy on floor 1 and needs an assignment. Please text me the details so I can hand them over." Now we have dynamic ARP inspection, DAI, an advanced layer 2 security feature that prevents ARP poisoning or spoofing attacks, where a malicious actor sends fraudulent ARP replies to trick devices into rewriting their ARP caches and routing traffic through the attacker's machine. DAI secures the network through 2 core validation mechanisms. DHCP snooping validation check. DI intercepts every ARP request and reply on untrusted ports and cross-references the source MAC and source IP inside the ARP payload against the DHCP snooping binding database. If the pairing matches the database, it passes. If an unauthorized device tries to claim an IP that does not match its bound entry, the packet is instantly dropped. So ARP acts as a local translator that maps a known layer 3 IP address to a physical layer 2 MAC address. When a computer wants to communicate with a local device, it broadcasts an ARP request asking who owns the target IP. The matching device replies with its hardware MAC address, allowing the sender to save the mapping in its ARP cache and physically transmit the data across the network. So we also have ARP ACLs for static devices. Because static devices like servers or printers do not use DHCP, they are missing from the snooping database and will normally be blocked by DAI. To fix this, engineers create manual ARP access control lists, defining legitimate MAC to IP pairing, forcing DAI to validate static hardware against these templates first before checking the dynamic database. So, the ID verification counter metaphor. DAI acts like a strict security guard check-in desk at an airport. If a passenger walks up and says, "I'm the pilot of this plane, let me through," the guard doesn't just believe them. The guard looks down at an official master manifest sheet generated by the Central Operations, the DHCP snooping database. If the passenger's face and name aren't on the official list, they are detained immediately. VLAN attacks and tenant isolation. VLAN security vulnerabilities in private VLANs describe how attackers exploit trunking behaviors to bypass logical network boundaries and how engineers isolate multi-tenant traffic. Switch spoofing, unauthorized trunk creation. The attack. If an edge port is left in a default dynamic state and an attacker can send forged DTP frames to trick the switch into forming a trunk link, granting attacker access to traffic across all VLANs. Mitigation. Force ports into access modes using switch port mode access and disable negotiation with switch port no negotiate. Double tagging attacks. The an attacker on the native VLAN sends a packet with 2 stacked 802.1q tags. The first switch strips the outer native VLAN tag and forwards it across the trunk. The upstream switch reads the second inner tag and delivers the packet to the victim's target VLAN. Mitigation. Avoid using default VLAN 1 as the native VLAN. Instead, assign an unused dummy VLAN ID or globally force native VLAN tagging. The apartment complex metaphor. We're going to talk about private VLANs now. So PVLANs for tenant isolations. PVLANs partition a single primary IP subnet into isolated subcompartments to prevent hosts from scanning or attacking each other using 3 hardware layer port roles. Promiscuous ports. The master uplink like a router firewall interface that can communicate with all other ports in the PVLAN structure. Isolated ports, ports that can only talk to the promiscuous uplink. They are completely blocked from communicating with other isolated port on the same subnet. And you also have community ports. Community ports grouped together that can talk to each other and the master uplink, but are blinded to all other separate communities. Is that a phone call? Hopefully you just skipped. So PVLANs. Did I talk about PVLANs? So PVLANs are turn a standard shared room into a secure apartment complex. The promiscuous port is the main front entry door to the building. Anyone can walk through it to go outside. Isolated ports are individual apartment rooms. The tenants inside can walk out the front building door, but they can never knock on each other's interior walls or enter each other's private spaces. That was a pretty good analogy. So, private VLANs, port association and VLAN types. So private VLAN structure requires a hierarchical configuration dividing a single network into two distinct types of VLANs to enforce layer 2 isolation boundaries. Primary VLAN, the master umbrella domain that establishes the overall layer 3 subnet boundary for the entire architecture. There is only one primary VLAN per structure, and it serves as the exclusive link to the default gateway routers. Secondary VLANs, the sub-compartments nested inside the primary VLAN that control layer 2 isolation. They must be explicitly isolated within the primary VLAN are split into two types. You have isolated VLANs, a highly restricted domain where devices can never communicate with one another. Only one isolated VLAN can exist per primary VLAN structure. And you also have community VLANs, a group-based domain where devices within the same community can communicate freely but remain blocked from all other communities or isolated zones. Multiple distinct community VLANs can exist under a single primary VLAN. So traffic flow rules and port restrictions. So outbound from the promiscuous port to the promiscuous port is allowed. The community is allowed, to a different community is allowed, to isolated is allowed. Outbound from the isolated, you can talk to the promiscuous, but you can't talk to anything else. Outbound from the community, you can talk to promiscuous, you can talk to other VLANs within that community, but you can't talk to a different community and you can't talk to another isolated community. Cool. So for private VLANs, we have the folder and subfolders analogy. Think of primary VLAN as a master shared corporate Google Drive folder. Anyone in the department has access to this folder. Inside of it, you create secondary folders. One folder is labeled the isolation bin, isolated VLAN. If you drop files in there, nobody else can see your file, only the boss. The other folders are labeled marketing team or finance team, community VLAN. People inside those specific folders can share files with their immediate teammates, but they can't look across the other teams' folders. So this is a command that I used in the actual case study of when I was creating these private VLANs. So yep, I go into further detail in that video. Now the final thing that we're going to look at is access control lists. So the three ACL tiers defined. So you have port ACLs, apply directly to the physical layer 2 interface. It filters traffic entering or leaving that specific physical wire regardless of what VLAN the traffic belongs to. ACLs only support inbound filtering on most standard platforms. So from the gateway to the switch, not from the switch to the gateway, or from edge devices into the access layer switches. VLAN ACLs, VACLs, VLAN map applied globally to an entire VLAN broadcast domain. It inspects all traffic bridged within the VLAN or transitioning through it. It doesn't care which physical port the frame came from. VACLs are bidirectional by nature, but process traffic dynamically before it hits routing interfaces. Routed ACLs apply directly to layer 3 routed interface or switch virtual interfaces. So for example, interface VLAN 10, this is your traditional router ACL that filters packets trying to cross a layer 3 routing boundary. Our ACLs support both inbound and outbound directions. Default precedence and order of operations. Multi-layer switch ACL lookup order defines the strict sequential checklist executed by hardware ASICs when processing frames. If a packet fails an early gate, it is dropped immediately without evaluating downstream lists. Inbound traffic flow entering the switch. When a packet hits a physical interface, it must pass 3 consecutive gates. The PACL, the first gate evaluated directly on the inbound physical port. The VACL, the secondary gate checked at the packet enters the logical VLAN domain. RACL, routed ACL, the final inbound gate applied at the SVI or routed interface only if the packet needs to be routed to a different subnet. Then we're going to look at outbound traffic flow exiting the switch. When a packet leaves the switch engine, the evaluation hierarchy reverses. RACL, the first outbound gate checked as traffic exits the layer 3 routing engine via the egress SVI or routed interface. VLAN ACL, the second gate checks as the packet drops down the egress VLAN domain. And then port ACL bypassed. PACLs do not evaluate outbound traffic on standard layer 2 switch ports, allowing the packet to immediately exit the physical wire. So finally, we're going to deep dive into PACL operation modes, prefer port versus merge mode. ACL overlap modes describe how a Cisco switch handles conflict when a physical interface has a port ACL, PACL applied, but also belongs to a VLAN or chunk governed by a VLAN ACL or routed ACL. Cisco switches manage this overlap using 2 distinct operating modes. Preferred port mode rather, the rule that PACL becomes the absolute solitary authority if a PACL is configured on a physical port. The switch completely ignores any overlapping VACLs or RACLs for traffic entering that port. Use case, ideal for strict untrusted edge deployment where you want to enforce a hard security profile on a specific physical jack without letting global corporate VLAN maps interfere. Merge mode. The switch combines the rule of the PACL, VACL, and RACL into a single unified hardware lookup table inside the TCAM. A packet must pass the conditions of all applicable ACLs to be forwarded. If the PACL permits a packet but the downstream VACL denies that the packet is dropped. Use case, standard corporate campus environments where you Want to enforce a basic port level restriction like blocking a protocol at the desk while still allowing global VLAN security policies to monitor the rest of the traffic. Hopefully that makes sense. Now look at the airport security analogy. Treat the multiple ACL tiers like the security checkpoints at an international airport terminal. PACL is the initial TSA agent at the front door checking your physical flight ticket to let you onto the building. VACL is the heavy luggage X-ray machine scanner that looks at what you are carrying inside the main terminal hole. RACL is the passport control customs officer standing at the gate right before you step onto the plane to leave the country, across the layer 3 subnet boundary. If you fail at the front door, you never even make it to the baggage scanner, VACL. And here is the command that you would use for PACLs and RACLs, for example. Hello. I think my mic died for a bit, but I don't know where it died. So hopefully, I guess what you can do is, I think it would have been just this last bit, but I went through, you can just read it for yourself. I was just reading off the notes and adding a few notes, but nothing really major. But I just wanted to say that I'm going to be creating. Hello. So yeah, before my mic dies, I'm going to be creating PDFs, uploading into my GitHub, and I'm going to be going back. Hello, hello, hello. Thank you very much for watching. My mic is about to die. Yep, leave a testing. See you in the next. Bye.